A top AI model scored 10.6% on a new visual benchmark. Humans scored 96.1%. The gap tells us something unexpected about how AI actually sees. A new paper just dropped on ArXiv with results that are genuinely startling. The benchmark is called ActiveVision, and it tests frontier multimodal models on a task that seems almost trivial for humans. GPT-5.5 at its highest exposed reasoning effort level solved only 10.6% of the items. Claude Fable 5, which the paper notes tops most reasoning and coding leaderboards, managed just 3.5%. 3 human participants averaged 96.1%. That is a gap so wide it almost looks like a typo. The benchmark was introduced in a paper titled An Exam for Active Observers, authored by Jiarui Zhang and 5 co-authors. The authors designed ActiveVision with 17 tasks spanning 3 categories, all built around one core idea: force the model to look at things more than once. Human vision is a closed loop. We shift our gaze continuously, guided by intermediate hypotheses about what we see. Decades of psychophysics and cognitive science have argued that this active observation is essential for a wide range of tasks. Current benchmarks mostly ask models to describe a single static image. ActiveVision makes active observation measurable for the first time. The failure patterns are specific and revealing. GPT-5.5 scored 0 on 11 of the 17 tasks. Claude Fable 5 scored just 3.5% across the board. Both are considered frontier models. The paper emphasizes that the interesting finding is not that a vision model failed a benchmark, because that happens weekly. The interesting finding is the specific shape of the failure. These models are not just slightly worse than humans. They are failing in ways that suggest a fundamental gap in how they process visual information, not just a lack of training data. Active observation means looking at something, forming a hypothesis about what you see, then directing your gaze again based on that hypothesis. It is a loop, not a one-shot. When you read a schematic or inspect a complex diagram, you do not take it all in at once. You scan, infer, scan again. The paper argues that current multimodal large language models largely lack this capability. They receive a fixed set of visual tokens and reason over them. They do not actively choose what to look at next based on what they think they see. Here is where it gets even more interesting. The authors tested whether models could patch their own failures by writing and running their own vision code. They could not. The code produced by the models was unreliable on realistic imagery, and catching the errors in that code required the very active perception the models lacked, so you have a double failure. First, the model cannot see well enough, then it cannot write code that sees well enough. And then it cannot even debug its own code, because that requires the same active observation it is missing. The community reaction was thoughtful. One commenter called the benchmark shockingly clever and well executed. A commenter pointed out that the types of problems suggest the ability to read schematics and engineering drawings, which has good commercial relevance. One of the paper authors even showed up in the comments to say thank you for sharing. Several commenters noted that vision remains a huge weak spot across all large language models, and that this gap makes working with 3-dimensional assets and visual verification a major pain point for real workflows. Another commenter highlighted the language first vision second class structure of current models as a key limitation. The paper concludes that current multimodal models lack robust active visual observation and motivates new architectures and training objectives that close the perception reasoning loop. Several commenters connected this to the broader question of artificial general intelligence. One commenter noted that vision is the next big frontier to AGI, particularly once systems develop recursive self-improvement capabilities. The data so far suggests that giving models bigger language models or more reasoning tokens does not close the gap. The architecture itself may need to change. The ActiveVision benchmark forces us to confront a simple fact. Even our best models are not doing what human vision does naturally. They do not look, infer, and look again in a tight loop. Until that changes, scaling up model size and reasoning depth will only get us so far. The paper is available on ArXiv under the identifier 260716165. If you want to dig into the 17 tasks and see exactly where each model broke down, the project page linked from the paper is worth exploring. Thanks for watching, and subscribe for more deep dives into AI research. Thanks for watching. If you found this breakdown useful, hit subscribe and join us next time when we dig into another paper that reveals something unexpected about where AI really stands today.